1.5 or 1 1/3 talks on verification and robustness. So just to remind everybody, this is we're looking forward in this workshop. We're looking at a bunch of things that still need to be worked out. So that's the role of verification and robustness.
Thank you, everyone, for being here, and thanks to the organizers for inviting me. So what I'm going to do today is share with you a little bit about what's happening in the world of verification, formal verification, for deep learning systems. And I have to start out by prefacing that I'm not a machine learning person, not centrally from the ML community. I'm also not a traditional theoretical computer science person. And so what I'd like to do today is share some of the work that's going on in a different community, which is the formal methods world. And at the end, I want to be able to bring up a few directions and questions that I think would benefit the area of verification for deep learning systems. And I think the community working on theory of deep learning would be the right people to contribute to this. Okay, so, and I'm going to present today a selection of work. So rather than going deep into any one contribution, I'm going to give you more of an overview of a few different topics. And this is work done with several excellent students and postdocs and colleagues. Okay, so the context here is that, as we all know, there's a growing use of machine learning, and particularly deep learning, in safety-critical systems of all kinds. And autonomous vehicles, self-driving cars are a good example of this. As we see more and more deployment of deep learning in these systems, there's also growing concerns about safety. And as we all know, there's numerous papers showing that deep neural networks can be easily fooled. And there's also been serious accidents involving potentially the failure of perception systems used for object detection and classification. And as we know, deep learning has been extremely effective in perceptual tasks. And there's a good chance that deep learning was involved in some of these. So the particular angle with which I come at this problem of ensuring safety and high levels of assurance is from the area of formal methods. Now, I know that not all of you may be familiar with this field, so let me just introduce what it is. So the field of formal methods is really at the core about computational proving. So it's about algorithms used to prove theorems. And primarily, these theorem proving techniques are used for modeling, mathematical modeling, design, and analysis of systems. And primarily in formal methods, you can think of the tasks that we do as falling into one of three categories. So there's the task of specification, formal specification, which is writing down mathematically what the system must do or must not do. Then there's the verification task, which is once you have a spec and then you have a system description, you're essentially trying to understand whether or why the system meets the spec. Okay, so for instance, if a system does not meet the specification, we really would like to get a counterexample or error trace that explains to us why it goes wrong. And then the holy grail in formal methods is to do correct by construction synthesis, which is you start with a high-level specification, and you'd like to be able to automatically generate an implementation that is provably correct. And we've seen in many different domains that as there's a need for higher levels of assurance, there's increasing interest in formal methods. A particularly good success story for formal methods is that of digital circuit design or processor design, where today pretty much every digital circuit or microprocessor that is taped out goes through some levels of formal methods along the way. And so in the context of this Simon's program and this workshop, we're looking at deep learning systems. And by this, I mean not only deep neural networks, but also the systems that use deep neural networks as components. And what we are interested in doing is trying to address the design challenges of these systems. So a few years ago, we tried to understand from a formal methods perspective, what are the special challenges that AI-based systems, particularly deep learning systems, bring for formal verification. And so what I'd like to do in this slide is walk you through that to give you an idea of what we think are the challenges from the formal methods perspective. And then I will try to zoom into something more specific. So what you see here on this slide is the typical picture of formal verification. So what happens is you start out on the left with 3 inputs. So you need a model of the system under verification, S. You need a model of its operating environment, E. And then you need the specification of the properties that the system must satisfy. Okay? And then inside the box, we need a decision procedure that can answer this question, which is when you put together S and E, so you take the system and you compose it with the operating environment, does it satisfy the specification phi? Okay. And then you'd like to have a yes or no output. So either it says yes, indeed it satisfies the specification, and here's a proof, or no, it does not, and here's one or more counterexamples showing how things can go wrong. Okay. And in formal methods, there's been quite a lot of work expended on how do you solve these decision problems for particular classes of S, E, and phi. And typically, phi tends to be specified in some logic, but people have also used objective functions. And one of the most effective use cases of formal methods is in finding counterexamples and finding these corner case situations that lead to safety violations. Okay, so now when we look at deep learning systems, and I'm going to use throughout this talk, I'm going to use autonomous vehicles and the use of deep learning in autonomous vehicles as a way to make things more concrete. There are certain specific challenges that arise. So for instance, in the case of autonomous vehicles, it's incredibly challenging to model the operating environment of a vehicle. For the most part, unlike things like digital circuits or software, we don't really know what are all the agents in the environment, let alone have good models for how they behave. Okay, and that's going to be one of the first challenges for formal methods. The second aspect of this is that now if we want to do verification of these systems, we have to be able to deal with these large, complex ML models like deep neural networks, which are a very different beast when we think about the tools, the computational tools used in formal methods. And then a further challenge is that, especially in deep learning, one of the most effective uses of deep learning is in perception, but there is no formal specification for a perceptual task like, take an image and recognize whether there's a car in it or not, right? And so if you look at that little picture down there, that is actually a real car, but it's dressed up to look like a snail or a bug, right? And so how would you formally specify what it means to be a car, right? Seems like this is an impossible task. And so that, even coming up with the inputs is a challenge for formal methods. And then, after that, we have all the other traditional problems, which is now we have to search extremely high dimensional input and state spaces, like streams of images, which are, much higher dimensional than the traditional kinds of systems that formal methods has been applied to. And then if you want to do correct by construction, it's not at all clear where to start. All right. So seems like an incredibly challenging domain, and I think it's, in a way, it's good because there's enough problems here for the community to work on for at least a decade, if not more. Now I want to zoom in on what I'm going to talk about in this particular talk. Okay? And the main message here I want to convey is that at least for verification or for verified deep learning systems, the context in which the ML model is used matters a great deal. Okay? And so the picture I'd like you to have for this talk is the one right here, where we're really looking at the combination of the system under verification with the environment. And it's important to model the environment. Okay? So the deep learning, the deep neural network is one component of that system, but it's not the only thing. Okay? And there's a number of reasons why modeling the context of the deep neural network is important. Okay? So the first is that usually when we design these systems, like an autonomous vehicle, what you have are these top-level system-level requirements on safety that don't necessarily translate directly to the traditional notions of robustness that we often look at for deep neural networks. Okay? What we want to be able to do is start with these system-level requirements and make sure that those are guaranteed. Right? And so that connection between the system-level requirements and things you prove about the neural network, I think, is yet to be made. The second is that for adversarial analysis, we want to be able to model realistic environments and adversaries. And I think that more needs to be done to understand what realistic means. Okay? A third use case for modeling the environment is that it's actually useful to scale up verification. Okay? So if you look at the neural network that's processing images, the input is extremely high dimensional, but if you model the environment, you may realize that actually there's a much lower dimensional environment state space that is generating those images. And by modeling the environment, you can actually reduce the search over from the high dimensional space down to the latent lower dimensional space that comes from the environment model. And then finally, I think it's important for any engineering design to be able to understand what the assumptions are that the system is making about its environment. And so creating an environment model is a good start for that. Okay, so in the rest of this talk, I'm going to be looking primarily at deep learning for perception and looking at this in the context of what are called cyber-physical systems. So things like autonomous vehicles, which are combinations of computational systems and physical systems. Okay. So an example I'll use again and again in this talk is an automatic emergency braking system that uses deep learning for perception. And this is what it looks like. So imagine you have a car and it has a camera in front that's facing out towards the road. Let's also assume that this car is operating in an extremely simple environment. So if you see that picture up there, it's the straight road in the desert where there could just be one car in front, okay? One lane in each direction. And so the camera captures this image that goes into a deep neural network. The job of the deep neural network is simply to do a binary classification of whether there is a car in front or not. Okay, so either car or no car. That goes into a controller. The controller then sends its control input to the vehicle, which we'll, in control theory parlance, we'll call the plant, which then interacts with the environment, and that produces new sensor data. So we're looking at this closed loop model. And then the goal of the AEBS system is, if there is a car in front, then it should start actuating the brakes in a certain prescribed order. Okay, I'm going to hide the details of how the controller works, but the basic idea is when an obstacle is near, the AEBS system to start actuating the brakes so as to maintain a certain minimum safety distance. Over the 2 or 3 years that we've used this example, we've created multiple models in various simulators, and in our papers we have links to all of those. But in particular, we've been using real neural networks for object detection and classification. In particular, I'll be using the squeeze det system that's been developed here at Berkeley in much of this talk. Okay, so with that in mind, let me start off by talking about specification first. Right? So if I take a deep learning-based system, what are the properties that we must verify? Okay. The way I think about this is there's two kinds of properties here. There are those that you write at the system level, which is the entire AEBS system. Right? So it's not focusing on the neural network, but looking at the system that contains that. And what we find here is that the kinds of properties we see there are the typical properties that you write for these cyber-physical systems. So you have safety, liveness, stability, these sort of things. But at the component level, which is at the neural network level, there's quite a range of properties what people can write. And so robustness seems to be the most popular type of property people talk about. And there's a few variants there, and I'll spend a few more slides to talk about robustness. But there's also other kinds of properties people are interested in, like input-output relations. So if the input lies in a certain region, you want the output to lie in a certain other region. There's also things like monotonicity, fairness constraints, certain coverage goals with respect to whether neurons fire or not, properties like semantic invariance, that the output should be invariant to certain transformations on the input, and distributional assumptions, and so on. So in this talk, I'm not going to go through all of these. I'm just going to focus on system-level properties and on robustness. But if you're interested, we have a paper that describes this range of properties for deep neural networks. Okay, so robustness to adversarial inputs or mutations has seen a lot of attention, right? And so the kind of thing that I think we're all familiar with is you have an input and you make a mutation to that, and the mutated input produces an answer that is wrong. Okay. Now there's quite a range of definitions of what robustness to adversarial inputs means. And so one of the things we did several months ago is try to survey all the different variants of robustness and then give a common way to write down these local robustness properties. Okay, and so let me walk you through that. Okay, so in general, in local robustness, you're given an input x, so from capital X, the input space. And what you want to do is find another input x star such that three constraints are satisfied. Okay? So the first constraint is what we call an admissibility constraint. And so the idea here is that you want x star to lie in a subset of capital X, we'll call x tilde. Okay? So this defines the valid set of perturbations, or the allowed perturbations. The second constraint is what we call a distance constraint, which says that you can, even within x tilde, you're only interested in perturbations that are within a specified distance away from the original input. And then the third constraint, which we'll call the target behavior constraint, is really the goal of the adversary, right? What the adversary wants to do here. Okay, and so this is a decision formulation of the robustness property. Typically in the literature, what we found is people tend to write optimization versions of this. And there's, broadly speaking, two variants there. One is the one where you want to minimize the perturbation. So in this case, you want to find the closest x star to x that causes something to go wrong. Okay, and so in this case, you can say, well, your mu is your distance metric between x and x star, and you're going to bound that by some parameter alpha, and then you want to minimize alpha. The other one is you want to maximize some notion of loss, right? And so in this case, this is more about something in the target behavior constraint. So you have this loss function, and you want to be able to maximize beta. Okay? Okay, yeah.
I'm trying to understand the need for one, namely, why couldn't x tilde be defined as the points x star that satisfy two?
Okay, so one of the things we wanted to do is not to keep the admissibility constraint separate from a notion of similarity to the original input, right? So there are cases where you want to define the space of modified inputs not as being dependent on x, but as being from some space of allowed perturbations, right? And so it's just you're right, you could actually merge them, but we just felt in the sake of understanding the literature, it helps to separate them out. Okay, so this helps us capture all the local robustness properties, but one of the things that when doing this exercise, we felt is that there are certain things that local robustness doesn't quite capture, right? There are certain questions that remain. Okay, so for instance, um, you can define these mutations as being norm bound, right? So close to some to the original input. But first of all, can these mutations actually occur in practice in the environment? Okay, so if I'm looking at the deep learning system in context, then can the environment actually produce these sorts of mutations? Secondly, there could be mutations that the environment can produce that are big in the sense that the X star is actually quite far away from X in the pixel space. Right? But in some semantic sense, it's not so far away. So an example of this is if I have an image with cars in them, and I go and change the colors of all the cars, right? So now I'm making a transformations to a whole bunch of pixels, but I'm not really changing the semantics of the image with respect to, say, object detection and classification, right? And I still want my neural network to produce the same output, right, on this transformed image. And then the third question is, well, even if there was like an adversarial perturbation, what's the impact at the system level of that? Okay, so let's look at the first two questions. So this is what my collaborator Somesh Jha and I call semantic adversarial analysis, that we really need to be able to look at doing adversarial perturbations not on the concrete input space, but on what we'll call the semantic feature space, which is what produces the concrete input. Okay? So the picture here is that there is a space S, which we think of as modeling the environment, and then there's a process of rendering, right, that produces concrete inputs. And what I'm really interested in is a notion of semantic robustness, which is that if I take two semantic feature vectors, S and S prime, and these are things like the positions of cars, the models, the color, maybe the time of day, the position of the light source, things like that. Right? Those are your semantic features. And I take two semantic feature vectors that are close to each other. Okay? And now if I look at the X and X prime that are generated from S and S prime, I want the output of the neural network to be close on those.
So the render could be like the camera on the car, that's what you mean? But the render out.
The renderer, yes. So the renderer.
Like the camera on the car or something?
Exactly, yeah. So whatever takes the parameters of your semantic feature space and then produces an image from that. Yeah. Okay. So so that's what I want. I want something that can do semantic robustness analysis. Okay. Now, if I look at this pipeline up here, if the renderer R is differentiable, then I should be able to apply all the techniques from standard adversarial analysis to this, and basically be able to find adversarial inputs in the S space. Okay. Of course, differentiable rendering is a hard problem that many groups are working on, but there's been some recent progress on that topic, and so very recently, Somesh Jha and I, along with our students, got some results where we took the 3D SDN differentiable renderer that came out of MIT recently. And what we did was, if you look at the image on the top, you can see the bounding boxes on the cars over there. And so what we've done to produce the image, the adversarial input image down here, is we've applied the fast gradient sign method, so standard adversarial analysis technique, but on the semantic feature space, which is modeling this scene. And what you see, of course, is that we changed the color of the red car. And then we've also changed the time of day, so some of the shadowing effects and so forth are different. And what you see here is that now it misses this car entirely. So there's no bounding box around this one, where there was one up there. Okay? So the hope is as progress in differentiable rendering and things like that get better, we'll be able to take everything that we've done in adversarial analysis over the concrete space and be able to do things like this.
Sorry, I didn't understand. Just changing the color means it loses the...
Right, so changing the color of this vehicle and also changing the time of day. I think those are two things. I can't remember. Maybe the texture of some of the buildings also.
The time of the day I understand.
Yeah.
But I don't understand why the color would...
And I don't understand either, right? So this is some of the... this is just telling us that we were able to find this sort of adversarial input. And I think this is a realistic transformation, right, on the scene space. But now the question is, why did this happen? Why did the neural network miss this? And I don't understand that. Okay. So if there are people in the audience who can help us understand this, I would love to chat with you. Okay. I have another example coming up later in the talk, which has a very similar nature. Yeah.
But the equation you had in the previous slide,
Yeah.
the property, effectively says that if you have things that are close in semantic space,
Yes.
you want the predictions of the network to be similar.
That's right.
The question is, how do you capture that? On the one hand, first of all, how do you capture semantically similar?
Yes.
And second, you could of course train the networks in a semi-supervised learning way to add a loss that when S is similar to S prime, then f of x needs to be similar to f of x prime.
Yes. Yeah. So yeah.
In the example you were showing in 13,
Yes.
was the network trained with any of these semi-supervised losses in consideration or not?
So the answer is no, it was not trained with the semi-supervised losses. But to your first question, what is the notion of similarity, right? We were just using a standard norm bound, but in the semantic feature space, right? So
Yeah, but I think it's very hard because some changes are not small in RGB space.
Yeah.
And so what is going to be the feature space in which those changes are small?
Right. I don't have a good answer to that, right? Yeah, I mean, I think it's an open problem yet to figure out what are good notions of similarity in the semantic feature space. Yep.
So can you go back to the cars?
Yep.
So I'm nitpicking your example, but admittedly, if our goal is to try to understand why the network failed, the bottom image does not have a gray car. That is not a recolored red car turned into gray. If you look closely, there are all sorts of significant distortions in the back of the car. So I'm not saying that, I mean, of course, a perfect deep network would identify,
Yeah.
everything always, but this particular example is not purely a recoloring.
Yeah, that's true. So this is from the virtual kitty data set, right? And the top image is not an original vkitty data image. It's a re-rendered. So it actually it's gone through like an identity transformation through the 3D renderer. Okay, so and the reason is that the renderer does produce artifacts, as you see, right? And so we try to be as equal with respect to those as we could. Yes.
So I have a big problem with all this approach.
Yes.
Because on one hand, you produce synthetic examples on which the network fails, and there is no way to say that these are something that we should really worry about, or is this just an artifact of the way you generate the adversarial examples? So this is on one hand. On the other hand, even if you show that there is no such problems, you say nothing about real problems that you will encounter in practice, because maybe there is something that is not generated by your model.
Yeah.
So what exactly do you verify?
Okay, excellent question. And so I think this is a great segue into what I'll talk about next. So hopefully that'll answer that. In the interest of time, let me move on, and I'm happy to take other questions later. So the question really that came up in this last one is, why do I care? Like, what's the impact of an adversarial input on the system, right? And so really, I think what I showed you was that, hey, we need to go from standard notion of robustness to the semantic notion of robustness, but even that is not enough, right? And what I really care about is verifying this system level specification. So I'm going to take something very simple here. So what I'm really interested in is verifying the system containing the deep neural network. So go back to my example, that's the closed loop system. And I'm going to just write properties of that system in standard notation that's used in verification. So we use often a notation called temporal logic. And so what that expression says is that it's always the case at all time points, the distance between the ego vehicle, the autonomous vehicle, and any environment object is at least some threshold delta. And the key point here with this property is that it is not over the deep neural network. It's not a property over the x and y, the input and output of the deep neural network. It's over the other parts of the model. which we have well-defined mathematical models for. Okay, and so so here's that closed loop model, right? So SE is the state of the environment, X is the image, that's the input to the neural network F, Y is the output, the control input is U, and the plant state is S sub P. And that same property is of the following form. So it's for all time points t, and the state of the environment, the state of the plant, all of these are functions of time. And now I have the safety predicate, which in the previous slide was that the distance should be at least delta, right? So I have the safety predicate that should hold at all time points. Okay, that's the kind of property that I want to verify. Okay, now the kind of property we have is a fairly standard property for verification. The new challenge posed by the use of deep learning is that typically, in order to do verification, you have to do what is called symbolic evaluation, because you're trying to verify for all inputs, for all x, right? And so what you want to be able to do is be able to evaluate f for all possible x. And symbolic evaluation of these deep neural networks is just not computationally feasible at this point. So the question is, how do you actually get verification to scale up? Okay, and in the work that we've been doing, we've been applying fairly standard principles from the verification literature. So the first idea is abstraction, which is we're going to try to replace the deep neural network by a simpler approximation, and then do the analysis with that approximation, and then use those results to be able to say something about the original system. And the second is what we call as compositional reasoning, which is you'll break things up into components and try to break up the verification task into component verification tasks. Okay, so in the cyber-physical systems world, we know how to verify safety properties of these kinds of systems. Okay, so the difference between this picture and the one I showed you before is there is no sensor that's capturing images, and there's no deep neural network. Right, you directly have the environment state fed into the controller. All right, and so it would be great if we could take our more complex verification problem and reduce it to solving one or more of these. Okay, then we can just use as a subroutine all the work that's happened already in the verification world. And so this is how we do it. We start with what I call the CPSML model. So this is like the closed loop model with the deep neural network in it and the property phi. And the first step we do is we abstract the deep neural network away from the model. And we started with something very simple. Okay, so what we do is we replace the neural network with two approximations. Okay, one we call an over-approximation, and the other we call an under-approximation. The idea here is that an over-approximation is something that is like a conservative assumption. So in particular, the most conservative assumption you can make about the network, about its behavior, is that it's always wrong. Okay? Now, note that in this case, we actually have a model of the environment. So we know what ground truth is, right? So if there is a car in the image, right, the environment model would say that. And so in the over-approximate case, the idea is that if your environment model says that there's a car in front of the camera, your approximation of the neural network will say, no, there's no car, right? So it's always giving you the wrong answer. The under-approximate one is the perfect classifier. So it knows exactly what the ground truth is, and it always outputs that. Okay? Now, the true behavior of the neural network is somewhere in between. But by looking at these two extremes, what we're able to do is compute what I call the region of uncertainty. Okay? So this is basically a predicate over the state of the environment and the state of the vehicle and the control inputs that tells you, if these are the values of SE, SP, and U, and the decision of the ML model flipped from being wrong to being correct to being wrong, then my safety property would be violated, right? So it's really telling you what's the states in which the decision of the ML model matters. And what we do there is we take that and then we project that to the ML feature space. So we try to find out, here's the region of inputs to the neural network that correspond to this region of uncertainty. And then we can invoke our favorite adversarial analysis technique, but now only focusing on this subset of input space. Okay? And we can produce misclassifications, which we then combine with analysis of the rest of the system to produce full system counterexamples. Okay? if at this point we find a counterexample, we can output it. But if we don't, then we have to go through a step of what's called refinement, which is basically going from our highly approximate, these over-approximate, under-approximate models to something that's more realistic and in between. Okay, so let me give you an example more concretely of what happens here. So this is going back to the ABS example. So in this very simple case, the two state variables we will look at are the initial relative velocity between the ego vehicle and an environment vehicle, and that's on the x-axis, and the initial relative distance between the ego vehicle and environment vehicle, that's on the y-axis. And what you're seeing here in the colors is that everything in the green region are combinations of initial relative velocity and initial relative distance where the safety property holds for a certain period of time. And everything in the red region are combinations where the safety property is violated. Okay, so that means it gets within the minimum safety distance. And this particular picture that you see here is for the case where the ML model is perfect. So it's always giving you the correct ground truth answer. Okay, and so in particular, you have these red regions, which are cases where the initial relative velocity is, in this case, very high, and the initial relative distance is quite low. And so it doesn't matter if the classifier is correct, you're too close to the environment vehicle to avoid a collision. Okay. Now we do the same thing for the case where we have the pessimistic ML model, so the thing where it's always wrong, and you see that more of the green turns into red. Okay. And so now what we're interested in doing is taking a difference between these two pictures, and so that's the yellow region. Okay. So using existing verification techniques, we can actually compute these regions, and so we can take the difference between these two, and that's basically all combinations of initial relative distance and relative velocity that where if the ML model produced a misclassification, that could lead to an unsafe state. Okay? And so what we do there is we take those combinations and then we concretize them by producing images that correspond to those. Okay? All right. So that's the idea. You're taking these models where you've abstracted away the ML model, right? And then we apply our traditional verification techniques to compute these regions. And then once we've computed the regions, we can go back and say, okay, now what is the feature space that we need to focus on? Is there a question?
Why is the ground truth curve not smooth?
Which one?
To the left, the leftmost
Yeah.
picture. So that's just ground truth, right? That's just like you're specifying the requirement.
Yes.
How did you get that
How did we get this?
curve?
But it depends on the dynamics of the vehicles in your model, right? So it depends not just so what we're seeing here is anything in the red region here is basically
That makes
yeah.
sense, but I'm just wondering why the curve is not smooth.
Why is it not smooth?
It's
Okay,
why is it-
I think it's just an artifact of the way it's computed and plotted.
Okay.
Okay, so so what can we do with this? So once we're able to compute this yellow region and then produce these images, what we can do is do a search, a more systematic search over that the space of all images corresponding to the yellow region, and that's what you're seeing on this slide. And so in particular, there's 3 dimensions along which we generate images there. So one is what I call the x dimension, which is the lateral dimension here of moving an environment car along the direction perpendicular to the road direction. The z is along the road direction towards the camera or away from the camera. And then this axis is the brightness of the image. So just to keep things simple, we have 3 axes of modifications. So you can think of these are all modifications to the semantic feature space. And what we find here is that maybe according to intuition, as we increase the brightness of the image or as we move the environment car away from the camera, the number of misclassifications increases. And indeed, you get images like this, which on the screen is really hard to see. But there's an environment car way over there, and it's a very bright image. But what we also find are things like this. So it may be hard to see in the back, but there is one misclassification here in a sea of correctly classified images. And this turns out to be the following image, where there's a car that's slightly driving on the wrong side of the road, but close enough to the ego vehicle that if it's missed, it would lead to a collision. Okay?
So the yellow region seems to be the spec that you found in which you want to test or verify a network. But I'm guessing it's still not possible to do an exhaustive search in that region, right? Like you're still hoping that some points that you pick up are is it an exhaustive search in that region, or is it more like looking at some samples in that region?
Right. So so that region is a continuous region, right? And so in practice, what you'd have to do is you have to grid up that region with a fine enough grid, and then we do an exhaustive search over that grid. Right? If you wanted to do a search over the continuous region, then we need symbolic techniques that can do that. And as of now, at least for the kinds of dynamical models we have, those techniques don't scale. Okay. All right. So that was actually one of our first results from more than 2 years ago, and then we were able to extend the same technique to streams of images. So here it's the same kind of situation. So you see here on this road, there's green dots and red dots, and every dot is a location where an environment car is placed, and the red dots are cars that are missed, and the green dots are cars that are correctly detected. And we found, in particular, this is using SqueezeDet, which is trained on the Kitty data set, and we find alarmingly lots of cases where it misses cars that are close to the ego vehicle. And then we can confirm that in the closed loop simulation, those could lead to an unsafe state. Okay. And so the idea here is now we're able to, because of using abstraction, we can sidestep this challenge of searching this high dimensional space by instead doing our analysis on the abstract models, and then use a separate adversarial analysis technique to search through the image space efficiently. Okay. One of the next steps, obviously, is if we can generate lots of counterexamples, then we'd like to be able to use them to retrain the neural network. So this is very similar to the work in adversarial analysis, where you can use those adversarial examples to retrain them. The one difference between this work and the work in adversarial analysis is that here the examples that we're adding back into the data set or using to augment the data set are those that violate the safety specification at the system level. So they're not really examples that violate local robustness, right? But instead they're counterexamples to safety. And what we've seen is that by being careful about which of these counterexamples you add back to the training set, you can substantially increase the accuracy of your ML model. And you can also retrain until you don't see any safety violations.
When you say that you increase the accuracy,
yes,
with respect to what? I mean, you don't have a good model of the environment. So how do you measure accuracy?
Yeah. So with respect to that bullet, what we do is use measures that the object detection literature commonly uses. So here we start with an existing data set, right? And we are measuring accuracy using mean average precision and other metrics. And what we're showing here is by adding back counterexample images, we're able to improve accuracy with respect to those metrics.
At mean average, it all depends on the distribution of instances of.
Yeah. So this is empirical, right? So this is over the empirical data set, right? So there is with respect to bullet number 3, there's a disconnect from what I talked about earlier, which is where it's not based on the environment model. But bullet number 4 in this is really the case where we do have an environment model and we are retraining until we don't see any safety violations. Right. Okay. So let me conclude very quickly. The other thing that we've been doing in the verification world is coming up with ways to model the environment where the semantic feature space can be quite large. And it's hard to model that as a large feature vector. And instead, we'd like to give the user a more programmatic way to write these models. And so what we did was design a programming language, a probabilistic programming language called Scenic, that allows you to define distributions over scenes. So this language is currently focused towards describing 3D scenes of agents along with models for those agents. And of course, it has use cases like just being able to use that as a way to describe your environment and use it with a simulator or a renderer to do data generation. But we can also use this as a language for verification. So just to give you an example, here's the code for a Scenic program describing the scenario of a badly parked car. And what you see down here are, from this program, images that we have generated using the Grand Theft 5 auto rendering engine. So in the interest of time, I'll skip over what Scenic, what the syntax is, but the idea is for every scene, there's an ego object. In this case, it's a car itself. And then we describe locations that can be picked according to some distribution, right? So in this case, there's a curb region, and we're picking a point uniformly at random from that curb region, and we're placing a car at a badly parked angle there. And so we're really describing a distribution over all of these scenes, and then the back end is doing a sampling from that in order to generate these images. And so we're able to use this to describe fairly broad scenarios with complex structure like platoons and bumper-to-bumper traffic. But the one thing I want to talk about here is we can also use it to debug issues that come up with deep neural networks. So for instance, here's an image that we synthesized using the GTA engine of this car with a racing stripe on it. And then we ran the SqueezeNet network on it, and it reported that there are 3 cars where there's just 1. Right? And so this is a case where, and the confidences are also reasonably high. It's hard to read them. And so the question here is, why did SqueezeNet do that? Right? And similar to the question that someone asked earlier. And so one thing that we can do now, if we have a programmatic way to generate these scenes, is that we can do systematic debugging by varying parameters of the scene in a systematic way. Right? So we could change the model of the car. We can add noise with respect to its position. We can change the environment around the car. We can do all of these things, in fact, automatically, and then see what happens, right? And see if the same failure scenario comes up again. And in this particular situation, we thought it was the racing stripe, and it turned out that it was none of the ones at the bottom here. In fact, it was just the distance between the camera and the location of the car, right? Which I still don't understand why that was the problem for SqueezeNet. Anyway, so that's the Scenic language and what it allows us to do. Okay, so to conclude, yeah.
Just a quick question about Scenic. So does
Yes.
Scenic have the conditioning operator?
Yes.
Okay, so,
Yeah.
so in some sense you can also tune your rendering model based on the real world data that you see.
Yeah, absolutely. Yeah, you can place constraints. Okay, so one of the things we've done over the last year or so is actually implement all of the work that I talked about and a few more things in an open source toolkit that we call Verify. And it has a number of use cases, including you can do things like property-directed parameter synthesis. So you can try to automatically generate hyperparameters or model parameters so that once you train your ML model, the resulting system satisfies some safety properties. So let me give you one example of something that we've done with the Verify system. So this is a scenario of having an autonomous vehicle navigate around a stalled vehicle. So the maroon car on the left is the autonomous vehicle. It's approaching the stalled vehicle, the green one, which is demarcated by a bunch of cones. And the way this works is that the autonomous vehicle has a camera in front. All of this is done in the VBot simulator. And this camera image is fed into a neural network whose job is to estimate the distance between the camera and this sort of a quote construction site. Okay, and so what the car is initially doing, it's doing lane keeping, and once the neural network reports that the distance to this sort of a site is less than 15 meters, then it's going to switch to a lane change mode and try to navigate around that. Okay? And once the lane change is complete, then it goes back to lane keeping. So that's what we expect the behavior to be. So what we can do now is we can model this scenario in Scenic. So we can describe a random variable for the location of that site, for the location of the cones, for the orientation of the cones, for the color of the vehicle, the model of the vehicle, all of that stuff. And then we can run our verifier. Okay? And what I'm going to show you now is a visualization of what the verifier search is doing. Right? So initially, what the first simulation you see here is that it's a correct behavior of the system. Okay, the maroon car correctly navigates around that. But now, successively, you're going to see more and more simulations, and each one of them is really showing what the search of the verification tool is doing. So it tries to find behaviors that get closer and closer to a violation of the safety property. Okay, and at some point, the safety property will be violated. So let me see if I can get that.
We're quite over time, maybe.
Okay, yeah, let me, yeah, so this is almost the end. So I'll conclude after this. Okay, and so, what's going on here is very much the same thing that I talked about earlier with the abstraction-based example, okay, where we are combining the system level analysis with one that is doing a more detailed analysis over the ML model space. Okay? And it gets closer and closer to the point where it actually generates collisions. All right, so let me conclude here. So overall, I think what we've shown is that formal methods can certainly help in the design analysis of deep learning systems, and we have a bunch of open source releases that can actually integrate well with existing work on adversarial ML. And there's a number of other things that I think need to be done as well. One is to bridge between the simulation worlds and the real worlds, right? So a lot of the work we're doing here is in the simulation world, and so we need advances in things like domain adaptation to be able to train for the real world. We also need techniques for runtime assurance. So what I mean by that is anything that we do in design time verification always makes assumptions about the operating environment. And there's a good chance those assumptions will be broken at runtime. And so what we really need is ways to monitor those assumptions and have the system know that it's actually now in an environment where those assumptions don't hold. Right? And then you have to be able to take mitigating action. All right, so I want to conclude with a few questions and directions for the theory community that is motivated by our work. The first thing is I really feel like it will help, it always helps verification when the folks designing the systems design them in a way that makes it easy to verify, or maybe eliminates the need even to do verification of some kind, right? So we really want correct by construction design. And so one of the questions here is, there's all this work on adversarial learning in the concrete feature space. Can we extend some of those results to the semantic feature space? The second is, there's all this work on local robustness, but I think really there's a much broader set of properties beyond that. And what are the properties beyond local robustness that we can obtain theoretical guarantees for? Okay. The third, and this may be a segue into Zico's talk, is it would be great if we can impose constraints, ideally those that are drawn from formal specifications at the system level, on the training of the deep neural networks, or into the architecture of the deep neural networks, right? Ideally without sacrificing too much efficiency. Yeah, and I think some of the ideas that have been proposed recently, like semantic loss functions, are a step in that direction. And then finally, I talked a little bit about counterexample guided retraining, where you use a verifier to produce counterexamples and then use that to augment your data set. And you can think of the verifier as an oracle, right, that is answering queries, verification queries. And it would be nice to be able to prove results on the query complexity for particular domains, for particular classes of systems, at least. Anyway, so those are a few questions for the theory community, and thank you all for your attention. I'm happy to have a discussion afterwards.
So let's take questions offline, and then we'll start back up at 11:30.